of transporting ore from a mine at X to a factory at Y. And what you want to decide are which mines should supply which factories in order to minimize total transportation costs. So to formulate this problem mathematically, I'm going to think of the mines and factories as living perhaps in Euclidean space or on a manifold or maybe in a more general topological space, but always it's going to be a metric space with a complete separable metric. It's sometimes called a Polish space. And the distribution of production will be given by some non-negative, think of it as a measure, with the total mass would be 1,000 tons of ore, we can normalize it to be 1. So I have some non-negative measure mu plus that tells me where the stuff is being produced. And I have consumption, which might live in the same space or it might live in a different space, m minus, also a complete separable metric space. And I have a second non-negative distribution, m minus, that tells me where the stuff is being consumed. And then I have this transportation cost that tells you how much does it cost to move stuff from a producer at X to a consumer at Y. And I want to pair the points on the left with the points on the right so as to minimize total transportation costs. And I'm going to imagine that the total integral of this guy is the total integral of that guy. And so I'll normalize them both to be 1. So these are Borel probability measures. And there are different ways to formulate the problem, but the formulation that Monge was interested in 200 years ago was he wanted to find a mapping. Oops. G from m plus to m minus, which pairs mines with factories in a measure-preserving way. So this should be a Borel map. And whenever I have such a map and a measure mu plus, there's an image measure on the right-hand side, which I get called the G push forward mu plus. And what this image measure does is it takes a set over here. And so the image measure might look something like this. And the mass it assigns to this set V is exactly, you take the pre-image of V under the mapping G, and you ask how much mass does mu plus put on this set. Okay, so this was V, and that's exactly mu plus of G inverse V. And so that's the push forward of mu plus through G. And now what I'm interested in are which G's push forward mu plus to this given measure mu minus. So I seek so I somehow want to adjust G until the red curve over here matches the black curve. There are lots of G that do this, and so associated to any such G is a total cost of transportation coming from this guy. So I look at the cost of transporting from X to G of X, and then I weight that by the amount of stuff being produced at X. And this would be the cost associated with G. And Monge's problem was to try to minimize this cost among all G doing this. And actually, it's not so clear that the minimum is attained, so maybe I better write infimum. And this infimum is a number. It depends on c and mu plus and mu minus. And if c is something like a distance, then this number would quantify, in some sense, the discrepancy, the difference between mu plus and mu minus. So that's the problem we want to study. And basic questions are, when is the infimum attained? Under what conditions is it attained? If it's attained, is it uniquely attained? Sorry. Right. Is it uniquely attained? Can we characterize? Yes, there's a question? So just W is a number. It's just the value of this infimum. And if you change the measures or you change the cost, W will change. So it's a function of C and mu plus and mu minus. Can we characterize those maps that attain the infimum? Will it be will it be a continuous map? If these are manifolds, will it be a smooth map? And so on. So the question of smoothness is the regularity question that I'm going to spend some of the later lectures talking about. And so let me tell you a bit more about the kinds of settings in which one might be interested in this question. So often mu plus and mu minus will be manifolds, or maybe geodesic spaces. So we say what is a geodesic space? It's a space in which every 2 points, x0 and x1, have a sort of shortest curve connecting them. And that curve should have the property there should be this continuous curve that starts at x0 and ends at x1, and which has the property that at any intermediate points between 0 and 1, the points on the curve divide the geodesic into a ratio of s minus s prime to the entire distance between x0 and x1. Right? It follows from this that the curve will be continuous and start at x0 and end at x1. Actually, so this is the definition. What are the examples? Euclidean space with the Euclidean distance. The geodesic in question would be the straight line. And a second example would be a Ramonian manifold. And in that case, associated to any curve starting at x0 and ending at x1, you can compute the length of the curve by integrating along it. Of course, you can compute the length of a tangent vector x dot of s using the metric gij. And then you would integrate that from 0 to 1. And you would want to try to minimize that integral among all curves connecting x0 to x1 to construct a geodesic. And so in this case, the minimum turns out to be attained. That's the Hofferino theorem, as long as it's a compact or closed Ramonian manifold. And that minimum would define the distance squared between x0 and x1. And the curve which attains the infimum, which might be, say, this one here, will exactly have this property up here. So Monge was actually interested in the first problem, this one here. And that problem turns out to be hard, both because the cost function is not smooth at the origin and because it's not strictly convex. It turns out that, for example, this infimum is not uniquely attained even in one dimension. So in one dimension, you might imagine having a row of books on your bookshelf. That could be your mu plus. And you might want to move them one place to the right. So your mu minus would be the same thing translated one position to the right. And if you're trying to minimize the average distance that you have to move the books, you have a choice. Either you move each book one place to the right, and then the total transportation cost is the number of books times one position. Or you leave most of the books in place and you bring the leftmost book to the right-hand side, and then the total transportation cost is one book times n positions, and it's the same in either case. So this, for the first power of the distance here, the minimum is non-unique. It turns out things are a bit better if you look at powers other than one of the distance. So and it turns out that in this case, in Monge's case, he was actually not interested in one dimension, but he was interested in 3 dimensions. And it turns out that it's relatively hard in that case, partly because of this non-uniqueness, to show that there's a map that attains this infimum. So in the 1970s, a proof was given by Sudakov that the infimum was attained. It turned out that one of his claims wasn't quite correct, but it was correct in 2 dimensions, and it didn't work in 3 dimensions. And so starting in the late 1990s, people were able to give proofs in 3 and higher dimensions that this infimum was actually attained for Monge's cost. As I say, things were a lot simpler if you look at other powers of the cost. And in some sense, the Euclidean distance is a little bit like an L1 norm. If you look at a power p different from 1, the special case p equals 2 is a little bit analogous to the Hilbert space case. And we'll eventually see that for any p larger than 1, actually the minimum Monge's infimum is attained, and uniquely so. And it's also interesting to look at p less than 1. So here I have in mind either Euclidean or Ramonian distance. but I mean Ramonian manifolds without boundary.
Professor,
Yes?
I cannot see that color properly. Can you use continuity?
Black is better?
Yeah.
Okay. Thank you. So I want to say P less than 1 is also interesting, and this comes up in economic applications where somehow, you know, for example, if you're transporting something on a train, it's expensive to put it on the train. Once you have it on the train, okay, it costs more to ship things further, but it doesn't cost twice as much to ship something twice as far, and so you might think of something like the square root of the distance as a kind of model for that. And certainly, we may, in the notes, there's a detailed discussion of some economic applications, and we'll see if we get there or not by the end of the week. So there's another kind of interesting theme that has come up in this business, which is that to some extent, if I think about a situation where, like this one here, where both consumers and producers live in the same space M, and the cost is related, cost on that space is related to the distance, maybe some power. I can think of this number here as telling me something like a distance between two probability measures in P. And in fact, it turns out to be symmetric and to satisfy the triangle inequality if P is less than or equal to 1. And it turns out if P is bigger than 1 and you want this number to satisfy the triangle inequality, then you take the Pth root. And then this metric here tells you a way to measure distance between probability measures in M. And it turns out that this infinite dimensional metric space here reflects the geometry of the underlying metric space that we started with. So for example, if M plus equals M minus, and there's a geodesic space, meaning you have shortest paths between points in M, then it will also be true that given any two probability measures in M, you can find a path in the space of probability measures with this property here, except with D replaced by dP. So somehow I might have a finite dimensional manifold N with points on it. I can sort of lift the geometry to the infinite dimensional space of probability measures, and it turns out that there's an interesting connection between the geometry downstairs and the geometry upstairs. And some of that, so for example, curvature properties of the metric space downstairs turn out to be reflected in convexity properties of functionals on the space of probability measures upstairs. And part of that story was something that I developed together with Cedric Villani and Cordero Arauskin, and many other people have worked on that connection as well. So, let's see how I'm doing. Okay, so I give you some flavor for how things are simpler in P equals 2, and a prototype for the kind of theorem that we'd like to prove for general costs, characterizing the minimizer here. And So a sample theorem due to Brennan and others was able to give a very nice resolution to the question of understanding this infimum in the case where the sources and sinks live in Euclidean space and for the quadratic cost. And so here's the theorem. It says, I have any two probability measures for L on Rn, and the first one is absolutely continuous with respect to Lebesgue measure. Sometimes I'll call Lebesgue measure n-dimensional Hausdorff measure. Then there exists a convex function u on Rn such that the derivative of u viewed as a map from Rn to itself pushes mu plus forward to mu minus. And moreover, so that's point one. Point two is this map is essentially unique. There's only one mapping pushing mu plus forward to mu minus. I can rearrange any given mu plus to any other mu minus, subject only to the mu plus being absolutely continuous with respect to Lebesgue measure. And I can do it with a convex gradient, and there's essentially only one map that arises as a convex gradient. So up to mu plus negligible sets. And thirdly, it uniquely solves Monge's problem. i.e. for cost Euclidean distance squared. So it's a little bit like, it's a canonical way to reparameterize one mass distribution by another. So in one dimension, what would this map look like? What does it mean to be the derivative of a convex function in one dimension? Sorry? Monotone, exactly. So in one dimension, being the derivative of a convex function means you're monotone non-decreasing. And so it says if you have any two distributions on the line like this, like the black one and, the red one, say, there's only one way to move the black one to the red one such that you preserve the ordering of the points. And this, you can think of this as an analog of that to higher dimensions. And you can think of this property being the gradient of a convex function as being some kind of analog of monotonicity in higher dimensions. So, for example, I have characteristic functions of two sets, each with volume 1. I want to ask, is there a volume-preserving map from the first set into the second set, which is monotone in some sense? And the theorem tells me, yes, there's one which is the gradient of a convex function. You could also, in that sense, you could also think of it as being a little bit like an alternative to something like the Ramon mapping theorem. The Ramon mapping theorem says given any two sets in the plane, there's a conformal map between them. Here, we're asking for a different property. It's not conformality. It's this kind of monotonicity that comes from being a gradient of a convex function. But on the other hand, it doesn't just work in the plane. It works anywhere. And it doesn't just give me a map between sets. It gives me a map between any two mass distributions, mu plus and mu minus. So I understand that there are a lot of people at this workshop that are interested in partial differential equations. And so I guess the next thing that I'd like to do is tell you what what does this kind of problem have to do with partial differential equations? And this is the part where I get warm and want to take my sweater off. So the partial differential equations that this is connected to are nonlinear, but they're elliptic nonlinear equations. They're so-called fully nonlinear equations, and they're of what's called Monge-Ampere type. So let me explain how that works. Basically, this mapping G is acting as a change of variables between these two measures, mu plus and mu minus. So if mu plus and mu minus have densities with respect to, say, Euclidean or Ramonian volume, and if it turned out that this mapping G was a diffeomorphism, of manifolds, of the same dimension, then basically the Jacobian of this mapping, so the determinant of the derivative of G, the absolute value of that would be telling you the distortion between maybe a small set here and a small set there. Like a small ball here would go to an ellipse there, and this absolute value of the determinant would measure the ratio of the area of this ellipse to the area of this ball. And it's also supposed to be true that the integral of this black measure, which is to say has density F plus over the small ball, should equal the integral of this red measure, which has density F minus over the small ellipse. And so this ratio of the area of the ball to the ellipse should also tell me the ratio of the density F plus at x to the density of F minus at G of x. This is another way of writing the condition that G pushes forward mu plus to mu minus. At least for diffeomorphisms, where these derivatives are defined. And so I see in the case of Brenier's theorem, where I know G is the derivative of a scalar potential U, then what occurs inside here will be the second derivative, the Hessian of that U. And because U is convex, this Hessian will be non-negative definite. It will have real eigenvalues, and all the real eigenvalues will be non-negative. And so that in that case, I can remove the absolute values, and I get an equation for the scalar potential U. And so the equation would be determinant of Hessian of U at x is equal to the ratio of f of x, or I could move the f minus to the other side. And this is an example of a Monge-Ampere equation. For the unknown scalar U. And it turns out we'll see that if we linearize this equation around some solution U, the fact that U is convex exactly tells me that the equation is trying to be elliptic around that solution. Another, for example, if I take f to be 1, and I take f minus to be something like square root of, or 1 plus y squared to some power like n over 2, then maybe negative n over 2. Oops, I don't even need to do this. Then what's appearing on the left-hand side here is something like the Gauss curvature of the graph of u. And so we already see that there's some geometry going on here. If I can find a u that solves this equation, I can find a u whose graph has Gauss curvature f plus. And there's another beautiful application of being able to solve this equation to prove the isoparametric theorem, which I'm now going to show you. But let me mention that so far this was for g's which are diffeomorphisms. Now Brenier's theorem doesn't tell you anything about the smoothness of g, and it can't in general be a diffeomorphism. For example, if mu plus looks like that, and mu minus looks like this, so two lumps with 0 in between, there's no diffeomorphism that can take this continuous thing and map it and break it into two pieces. And so for this kind of situation, the solution guaranteed by Brenier's theorem is going to have to be discontinuous. And so that's telling you that the derivative of u is not even going to be differentiable because its derivative is going to have different values. Somewhere there's going to be a tear where the stuff on the left of the tear goes to this bump and the stuff on the right goes to that bump. And the u is going to fail to be differentiable along this tear. And so we can think of this condition here, which makes perfect sense even if u is merely convex, so its derivative is merely defined almost everywhere because convex functions are Lipschitz. We can think of this as being kind of a weak definition for solutions of this. So if you had a smooth function u and it solved this PDE, that would be great, but in some sense, any function u that does this is kind of a weak solution of this PDE here. I should have said there's an auxiliary condition in that acts like a boundary condition, which is that du of x should belong to the support of f minus for f plus almost every x. Right, that will be true if du is pushing forward mu plus to mu minus, so almost every point here will get pushed forward to a point there. And so when I'm looking for smooth solutions of this PDE, I'm going to have to impose boundary conditions, and they're going to look a little bit like this. So our first application, later today and tomorrow we'll talk about how to prove a theorem like that, but first let me sketch an application, which is a simple proof of the isoparametric theorem. So this is the Euclidean isoparametric theorem. It's the theorem that says if you have a set of given volume and you want to shape the set to have minimum surface area, the best you can do is take the set to be a ball. And so this is a very common, well-known theorem. In fact, people say it's even known to cats because the volume of a cat is constrained, and when a cat wants to minimize heat leakage, then it curls itself into a ball to minimize its surface area. So if I have two sets in Euclidean space, I'm going to take them to have the same volume. I'll take one set in Euclidean space. Here it is, m plus. And I'm going to assume the volume of M plus is the same as the volume of the ball, unit ball. So I'm going to take M minus to be the unit ball. And what I'd like to deduce is that the perimeter of M plus has to be larger than the perimeter of the ball. And so how am I going to do this? Well, Renier's theorem tells me that I can apply Renier's theorem by taking mu plus and mu minus to be uniformly distributed over the two sets. So I'll take f plus and minus of x to be the characteristic function of the two sets in question. And then Renier's theorem tells me, okay, there's a solution to this equation, determinant of Hessian of u is equal to 1. In that case, so 1, f plus will be 1. That will be determinant of Hessian of u. There'll be some convex solution to this equation. And so I can take the nth root. And since u is convex, as I say, this Hessian has non-negative eigenvalues, n of them. And so here I'm looking at the product, the nth root of the product of n real non-negative eigenvalues, and the domination of the geometric by the arithmetic mean tells me that the nth root of the product of those non-negative eigenvalues is less than the average, which is 1 over n, the trace of those eigenvalues. And basically, what I'm going to do is I'm going to integrate this inequality over the domain m plus. So when I integrate 1 over the domain m plus, I get volume of m plus. And this is less than 1 over n integral over m plus. The trace of the Hessian is the same as the Laplacian of u. And I'm still integrating with respect to volume, which is to say n-dimensional Lebesgue measure. But the Laplacian is the divergence of a gradient. And so I can use Stokes' theorem to make this a boundary integral. Of the gradient of u at x dotted with the outer normal to m plus at x. And now I'd be integrating with respect to surface area on the boundary of m plus. And, okay, the volume of m plus is supposed to be the same as the volume of the unit ball, which is the volume of m minus. I'd like to relate this to the perimeter of m plus, which is the n minus 1 dimensional measure of the boundary. And so what I'd like to say is the integrand is less than or equal to 1. Why should the integrand be less than or equal to 1? So this guy is a unit vector. So it's less than or equal to 1 in magnitude. It's the outer normal at some point over here. And gradient of u is taking values in the unit ball, somewhere in the unit ball. So gradient of u is less than or equal to 1 because this is the unit ball. So that was this condition here. It tells me that this fellow is less than 1. And so that's, the integrand is pointwise less than 1, and so that's less than 1 over the n, the perimeter of boundary of m plus. So now I have something relating perimeter to volume, which is good. And actually, in the special case where you happen to take m plus to be the unit ball, then I'm trying to minimize the same set to itself. What do you suppose is the map that? What do you suppose is the minimum distance squared distorting map from the unit ball to itself? So I'm trying to map a set to itself, and I don't want to move anything too far. What map am I going to use? Yeah. And Lonnie says, in this case, I'm going to use the identity map, because I don't have to move anything. So, and when is gradient u of x the identity? Well, it's the identity when u is 1/2 x squared. And in that case, the Hessian of u is the identity matrix. And then all of its eigenvalues are equal to 1. So both the geometric mean and the arithmetic mean are 1. And so in that case, I would get equality here. And also, in that case, on the unit ball, and a position on the unit ball, the outer normal is exactly equal to your position on the boundary. And so this guy would also be equal to x. And so I would have equality here as well. And so the whole chain of inequalities becomes an equality in the case of the unit ball. And it tells me that the volume of the ball is 1 over n times the perimeter of the ball. And so then now the whole chain of inequalities tells me that the boundary of m plus is longer than the boundary of the unit ball. So that's the proof of the isoparametric theorem. And this kind of strategy is very typical of the way that optimal maps are used to prove geometric and analytic inequalities. I mean, somehow, in the statement of the theorem, which I never stated, but the statement was that the perimeter of m plus would be larger than the perimeter of the ball. The statement seems very global, and it's hard to see how to use the geometry of the set in order to prove such a statement. And what this theorem of Brenier does is it kind of localizes the whole thing, and we can look at the local behavior of this mapping U, that somehow the geometry of the global sets m plus and m minus is captured by the choice of convex solution U to this equation. And locally, it's easy to see how to estimate, how to relate the determinant to the trace. That's just algebra. And then we take this local information, we integrate it back up, and we get the global information we wanted. So somehow this theory of optimal mappings is being used as a tool to localize global geometric information. And somehow the convexity, I missed a crucial hypothesis here. The convexity of solution U is critical in this story. On the one hand, it tells you that gradient of U is almost a diffeomorphism. And on the other hand, it tells you that these eigenvalues are real and non-negative, so that I have the inequality that I wanted. And it also allowed me to take away the absolute values that appeared in this statement here. Are there questions, problems, difficulties? Okay, so it turns out that in the original form, the problem is hard to work on because it's a very nonlinear problem. The cost function C is a nonlinear function of the mapping G. The constraint that G rearranges mu plus to give you mu minus is sort of, this determinant here is a very nonlinear functional of G. And so one of the things that makes this problem look hard is that it's nonlinear. It turns out one of the breakthroughs in thinking about problems like this happened in the 1940s and was due to Kantorovich, and it's quite closely related to the work that won him the Nobel Prize in Economics. And he was also thinking about transportation problems. Initially, he didn't know anything about Monge's work. And so he formulated a transportation problem of his own in a slightly different language from that of Monge. And it was in the language of linear programming. So, except infinite dimensional, unless you're dealing with measures consisting of a finite number of point masses, there are an infinite number of degrees of freedom in this problem. And so his idea was we can think of it as relaxing the constraints that every mine supply a single factory, which says that the output of all the stuff being produced at X has to go to a single point G of X, and replace that by allowing the possibility that a single mine distribute its output over many factories. So we want to replace G by a joint measure, gamma, on the product space. And so the picture is that I have, on the horizontal I have mu plus, and on the vertical I have mu minus. I have a certain distribution mu plus of mass that I want down here, and a certain distribution mu minus of mass that I want over here. And I want to try to put some non-negative measure gamma on the joint space. So the gamma of xy is amount transported from x to y. And I want, so you can think of gamma as being like grains of sand, and in some small ball here, the number of grains of sand would be, or in some small rectangle, the number of grains of sand in that rectangle would be telling you how much of the output of the interval down here is being consumed in an interval over here. And since this gamma is supposed to transport mu plus to mu minus, I want it to belong to the set of joint measures. So this is the set of non-negative measures on the product space that have the property that if I dump all the grains of sand over to the vertical, then what I see is the same distribution of grains on m minus as given by mu minus. Whereas if I take the grains of sand given by gamma and I dump them onto the horizontal, I project them to the horizontal, I want to see this distribution of mass, mu plus. So in other words, gamma of u plus cross mu minus should exactly be equal to mu plus of u plus. And gamma of mu m plus cross u minus should exactly be equal to mu minus of u minus. And this should be true, so this was the u plus, if you like, and that was the u minus. But this should be true for every Borel u plus and minus in m plus and minus. So the gammas belonging to this set are exactly playing the role of the maps G that pushed forward mu plus to mu minus, except instead of concentrating all the mass on some thin graph of a function G, I'm allowed to spread it out over the whole square. So this was 1942. Of course, I would still like to choose gamma to minimize my transportation cost. And so the cost associated to any one of these competitors, gamma, will be the cost of transporting stuff from x to y, weighted by the amount of stuff being transported from x to y. Now this is an integral over the product space. And that will be the cost of gamma. And the Kantorovich problem was to try to minimize this cost over all gammas in that set. And already, so notice that this functional here depends linearly on gamma. And the set of, if I have two gammas that satisfy these constraints, then their average satisfies these constraints as well, because these constraints are linear in gamma. And so this is a convex set. And so I'm trying to minimize some linear functional over a convex set. And so somehow the schematic picture for doing that I have some convex set down here. I don't know too much about what it looks like. So this is some convex set. I have some linear functional like that. And the idea is slide down the linear functional until you hit the bottom. And that bottom should be the minimizer. And this geometry, okay, the only thing complicated here is that my convex set is not sitting in Rn, it's sitting in some measure space. So where does gamma sit? Well, it sits in the dual of continuous functions on m plus cross m minus, in the Banach space dual. But as long as the cost C is continuous, the Banach-Alaoglu theorem, and these are probability measures, so it actually sits in the unit ball in this Banach space dual. And the Banach-Alaoglu theorem tells me that this thing is weak star compact, and this is a weak star closed subset of this weak star compact set, so it's actually a compact convex set. I'm trying to minimize some linear functional on it, but if C is continuous, then this linear functional will be weak star continuous. And so very abstract functional analysis tells us in that case, aha, the minimum's attained. I have a continuous function on a convex set, its minimum will be attained, and then I have an object that I can deal with. And so I can start to analyze, but it's still an interesting question. Is that object unique? I mean, when I slid down this to the bottom, did I hit a flat spot, or did I hit a corner? And can I characterize the object in some way? And so that will be the subject of the next lecture, is how can we characterize the minimizer of this linear functional on this linear convex set? It always exists, at least if C is continuous. You can always find at least one minimizer that's an extreme point. So even if it was a flat spot, that flat spot would have some kind of corners. But it's not clear if it's unique or how to characterize it. And the connection, which Kantorovich noticed slightly later, of his problem to Monge's, is once you have this minimizer, you can study the support of gamma. So this is the smallest closed set of full mass. And what you can, by the way, I should have said, and what you can hope is that the support of this gamma, instead of being spread out all over this product space, you can hope that the support of gamma actually concentrates in a thin set, maybe like this, which in this case, it would be a graph y equals g of x. So if all the grains of sand actually lived on the union of this and that, then I would actually be able to write it as some function over x, and then I would have a solution to Monge's problem. But not the opposite. I mean, looking from here for each y, there could be two x's. And so there's some potential asymmetry. Oh, and I should have mentioned, I also want to know this is non-empty for this minimum to be attained. So I need an example of a measure that satisfies these constraints. And gamma it contains the product measure, mu plus cross mu minus. So it's non-empty. But the product measure would spread mass all over this set here. And so it's very far from giving you a Monge solution. And so the question is, the product measure sits somewhere in this set, but can I show that it's not the minimizer for this linear functional? Can I show that the minimizer for this linear functional looks different? All right, so that seems like a good place to stop. Thank you very much for your attention.